Hey everyone, let's talk about cratered worlds. We're going to talk about the Moon and Mercury. They are similar, and we're going to compare and contrast them. So, talk about the general properties of the Moon, talk about the lunar surface impact craters, what they can tell us, the origin of the Moon, the planet Mercury, and try to compare Mercury to the Moon. So the Moon is the only other world visited by humans. What's it like? What can we learn from it? The Moon is geologically dead, so studying its surface can tell us about the early solar system, so that's why we want to learn about it. Mercury is similar to the Moon, so we generally lump them together when we talk about cratered planets or objects. But both of them can tell us about the history of the solar system because they have not erased their surfaces. They're basically dead, and everything that has happened to them is saved on their surface. So if we study their surfaces, we can learn about the history of what they've been through, just like the scars on us. So, general properties of the Moon. We want to discuss what has been learned from manned and robotic missions. We want to describe the composition and structure of the Moon. So the Moon is about 1/80th the mass of the Earth with about 1/6 the gravity. So you would weigh 6 times lighter on the Moon, which is why if you watch videos of astronauts jumping around, they look kind of silly. This gravity is too weak to hold on to an atmosphere. So the gas particles have too much energy, they just disappear. They just pop off the planet. When we measure the composition of the Moon and the environment around it, we find that it's deficient in what are called volatiles, which are materials that evaporate at reasonable temperatures. So, for example, alcohol, ethanol. If you take an alcohol swab or hand sanitizer, it just disappears off your hand. That's a volatile material. So the Moon, here's some properties. It's comparing the Moon and the Mercury together. The important one to pay attention to is this density. The planet Mercury is far more dense than the Moon. That means it's made of more heavier objects, okay? Materials, and we're going to talk about that. So most of what we know about the Moon comes from the Apollo program, which was the missions in the 1960s to send humans onto the Moon. The Soviet Union was the first to the Moon. They landed robots on the Moon, took pictures. It was a big deal. But the United States putting a human on the Moon was a big deal too. So these are a summary of the missions that landed on the Moon, except for Apollo 8 and 10, which were the attempts to practice the interception of the Moon and bring people back before they tried to land. And then, so Apollo 11 and 12, and then Apollo 13 actually did not make it to the surface because there was a explosion. And there's a good movie about that called Apollo 13. Sometimes they say, well, you know, why don't you take a picture of the lunar lander from space or Earth with a telescope? There's the lunar lander. Okay, the lunar lander is very small compared to the Moon. So you can imagine that it's very difficult to take a picture with enough resolution to see something like that on the surface. And there's a couple of dudes walking around there. All right, so this is a cool picture of the Moon. You can see the window of the craft here. And then this is from the Discover satellite. This is a satellite that orbits beyond the dark side of the Moon, basically. It's beyond the orbit of the Moon. And as the Moon passed in front of the satellite, it's a Earth monitoring satellite, it took this picture. So there's the Moon orbiting the Earth. Pretty cool. So some cool facts are that astronauts collected nearly 400 kilograms of moon rocks and brought them back to Earth in their pockets. Big pockets. They also left behind science experiments which continued to operate long after they left. They also took a lot of data from the orbiting craft. So the Moon is here. What they did was they had a rendezvous orbiter up here orbiting the whole time, and then they sent a spacecraft down onto the Moon while the orbiter stayed in place, and then they launched back up and intercepted with the orbiter before they headed back home. So someone was always on that. So that thing, while it's orbiting the moon, they didn't just sit there and wait. They were also taking pictures and data. So the cost of the Apollo mission was about $10 per American per year over 10 years. So it was about $100 per American over the course of 10 years, which is about the cost of a large pizza once a year. So if you're willing to pay that, that's cool. This is the Saturn V rocket. You can visit these. They are at various museums around the country, Alabama, Texas, and DC. They are monsters. They are giant spacecraft. You have to have a lot of fuel and a lot of thrust to launch out of orbit. There's a really great movie called Apollo 11, I think is what it's called. CNN Films or something produced it, and it's just super high resolution images and videos from the mission. It's a really good, just straightforward documentary about the program. Some cool footage I'd never seen before too. Okay, the moon has the same composition as the Earth's crust. This has implications for the origin of the moon, and we'll talk about that. The moon has no metal core. That's also a big deal. The moon's surface is rich with water ice. Okay, so think about this, what that might mean, that there's no heavy metals at the core. There's no core that's heavy. There's no, why is it made out of the surface of the Earth? Okay, so the lunar surface, we want to differentiate between the major features of the moon. There's light gray and dark gray parts to it. So when you look up at the moon, you see light gray and dark gray. And then we'll describe a history of that and then describe the properties of the soil. So the moon's surface is covered in craters. When you look up, you see that. The dark areas on the moon, people thought were seas from Earth. They looked at it, they said, oh, those dark areas, they could be water, could be an ocean up there. So, for example, the Sea of Tranquility, where the Apollo 11 mission landed, it is mare is the word for it. So if you order like frutti di mare from an Italian restaurant, fruit of the sea, so you'll get seafood. But this is what those areas are called. And the craters and the moons on the craters and mountains on the moon are very different than the ones on Earth. They're formed by different processes. So even though you might look at a crater or a mountain range on the moon, it's not from tectonic plates pushing up like on Earth. So some of those rocks that we collected from the surface, brought back to Earth for studying, we can measure from when they solidified to today, and that's between 3.3 and 4.4 billion years old. So that means since the Earth and the Moon formed 4.5 to 4.6 billion years, there was 100 million years or so where it was molten, and since that period, once it started to cool and then solidify, that surface ranges from 3.3 to 4.4 billion years old. So 3.3 billion would be the younger, more volcanic mare areas, and then the 4.4 billion years old would be the highlands and some of the original parts of the moon. So most of the moon is made of silicate rocks. For example, the lunar highlands, those are the oldest parts of the surface, and they are heavily cratered. Okay, so that's what this picture is on the panel over here. That picture is the lunar highlands, the most heavily cratered. Look at that. There's craters everywhere, all over the place. Craters on top of craters. So the Maria cover just 17% of the moon. So the highlands are about 83% of the moon, and then the dark areas are about 17% of the moon. They're much less cratered, indicating that they formed after the highlands and more recently, and then so they've experienced less impacts. They are from volcanoes and lava flows. So the surface is buried under a very thin, fine dust that the astronauts kicked up while they were walking around. That dust is the result of just countless impacts, and then it creates all this dust, and it slowly builds up this fine, dusty stuff. So there you can see a lot less craters. They're smaller craters than on the highlands up there. Okay, and then we've got some moon rocks here. So impactors, and there's a footprint. Humans walking on the moon. That's crazy. I'm gonna go. Come on, Elon. I want to go to the moon. Get that SpaceX rocket working. Okay, impact craters. So We want to compare and contrast ideas about how lunar craters form, and we want to explain the process of impact crater formation, discuss the use of crater counts to determine relative ages and lunar landforms. The main takeaway from this section, mainly, is how we can determine the age of a surface by studying it, and it encodes what has happened on the surface. So, importantly, it is actually difficult to differentiate between volcanoes and impact craters. If you see a crater, what caused it? Was it a volcano or was it an impact? So Earth has erased its history. Oceans, rain, erosion, tectonic movements, volcanoes, the surface is basically renewed pretty frequently. So it's difficult then to ascertain whether a crater is from a volcano or an impact. Well, I kind of missed a spot there. So Earth has erased the history, but the moon has not. So we can look through, by studying the surface of the moon, its history. But we need to be able to differentiate whether what's on the moon is from a crater or from a volcano, or from an asteroid or from a volcano. What happens when a rock hits the moon is it doesn't like just make a regular, like if you throw a rock in the sand, it doesn't just, make a kind of splattering like when you throw a rock in the sand. It actually blows up. So the crater is the result of an explosion more than the just displacement from an impact. Okay, so just because you hit the sand, for example, at an angle, you'd see kind of an irregular bloop, and the craters wouldn't be nice and circular. In this case, what happens, they come in so fast that when they hit, boom, it just blows up in every direction. So they make symmetric craters. So that's the important point here, is that by studying it, we can tell by looking at its properties whether it's from a crater or from an asteroid crater or a volcanic crater. The main thing is that was an area that took a while to develop, and now we're pretty good at determining the difference. So when a world has a low rate of geologic processes, we can use the crater count on the surface to get an estimate of the surface's age. So that's the main thing to take away from this. We anticipate, or we've learned, that a 1 kilometer diameter crater should appear on the surface of the moon about once every 200,000 years. And then there's the different diameters at different rates. So we can sort of estimate, if we just count how many of these craters we see, we could figure out how long it's been, okay, since the moon has been exposed to that. So that gives us an idea of how old the surface of the moon is, or how long it's been impacted on. So by comparing craters on the lunar highlands to the seas, we see that the rate of cratering dropped. So those maria, which happened later from the lava flows, they don't have as many craters on them. Okay, so that indicates that at some point the amount of impact slowed down, and that makes sense over the course of planets sweeping out crap out of the universe, pardon my French. Then there's less stuff to run into. So the longer we survive in the solar system, the less likely we are to hit something, because we sweep up all that stuff and try to get rid of it. So this is the rate of impact versus time, and you can see that we think that there was a lot more junk to run into, and when those highlands were getting nailed over and over again, after that there's the formation of the maria, and then we're here where the rate of hitting something is about constant. So it's not as common as it was back in the old days. And there's a meteor crater in Arizona, which is pretty cool. Okay, so the origin of the moon. Where did the moon come from? We want to describe the 3 top early hypotheses about the formation of the moon, and then summarize what we currently believe is the correct hypothesis for the moon. So there's 3 main ideas. One idea is that the Earth literally just split, and then you had the moon. That's called the fission theory. That's like nuclear energy is splitting the atom, or fission energy. So splitting the Earth. The sister theory, the moon and the Earth formed at the same time. and then that's just number 2. Or the capture theory, maybe the Earth grabbed the moon with its gravity and just the moon wanted to be a planet, but we wouldn't let it, and we just kept it in our orbit. Or the giant impact hypothesis, which is something hit the Earth, and then out of that collision, the moon formed. The fission theory doesn't work. The reason being, gravity holds things together. You would have to somehow explain Earth splitting and then the moon ending up over here. So maybe it was spinning really fast and then it just came apart. That doesn't make sense. We can't figure out how to make that one work. The sister theory doesn't work. You can't have the orbits that we have. It wouldn't make sense, number 1. And then if you look at the composition of the moon and the Earth, it doesn't make sense, because if they formed at the same time, they should be roughly uniform in what they're made out of, but the moon is mostly made out of Earth's crust. The capture theory, again, not enough. The gravitational dynamics of this don't work out. We can't, in our simulations, get a moon-sized thing to be captured by the Earth. The giant impact hypothesis is the current best guess. Okay, the giant impact hypothesis says something hit the Earth, and out of that collision, the moon formed. So this is a video of that. There you go, something hitting the moon, or hitting the Earth, and then, boy, look at this. It just, the amount of energy released melted everything, and out of this smudge of stuff, you're gonna see here slowly, you're gonna see a moon kind of forming. So this is a real simulation. This is not just some, weird thing. This is obeying the laws of physics, and you can see how after this collision, you could have something like this happen. Now, remember the concept of differentiation, where if you let salad dressing sit too long, it separates into its layers, like Italian dressing. Same thing, the Earth, the heavy metals sank to the center of it, and then when something hit it, it knocked off just the outer layers of the Earth, the crust and its mantle parts of it. And that's why the moon has no heavy metals in it, we think so far, because the moon is formed out of something that knocked off the outer layers of the Earth. Okay, so this is pretty cool. That's a long animation. Okay, so then let's turn our attention to Mercury. And Mercury, we want to talk about its orbit around the sun. We want to describe its structure and composition and explain this kind of idea with Mercury and the rotation, and then its features and Mercury's surface. And then, again, talk about its origin and evolution. All right, so Mercury, like the moon, it's the closest, it's like the moon, but it is the closest planet to the sun. It has the shortest period of orbit, 88 days. It has the highest average orbital speed. It's named after the fleet-footed Roman god, messenger. So having the highest orbital speed and the shortest orbital period, that's in line with Kepler's third law, right? It's the closest, so it should have the fastest. Its mass is about a 20th of the Earth. It's about half the diameter of Earth. It has a much greater density than the moon, which indicates that it has different compositions. Almost all of it is made out of heavier materials then. So that's interesting, right? It doesn't have a lot of that outer surface. Look how big its core is compared to its crust and mantle, which is very different to Earth, which had a core and that was that big, and then a mantle that was huge, right? So what we think about, and this is just showing you the craters on Mercury's surface. So what we think is, that's going to be the last thing in the chapter. For some reason, they push it at the end. We'll talk about its formation. Okay, so Mercury's day lasts about 59 Earth days. It's very hot on the hot side, very cold on the night side. This is because it has no atmosphere. So it swings from like 400 degrees to like minus 400 degrees or 200 degrees from day to night, because it cannot regulate its temperature. There's evidence that over time, as Mercury cooled and shrunk, it kind of buckled on its surface, which is pretty cool to think about these planets as just hot potatoes, or whatever. just cooling like anything else. So it's mostly metals. Its composition is mostly metals. Why not silicates? Oops. Most probably, this is what we think. Mercury, right? It has, if I go back to the schematic here, you could imagine that Mercury maybe was like this big, so then it more looked like Earth, where it had more crust and mantle material, and then its core was more of a normal proportion of the planet. But if you imagine something like the moon, how it formed, something hit Earth, you could imagine a lot of things hitting Mercury and just ejecting the outer layers, leaving behind over time just the heavy materials. So the lighter elements were knocked into space, and then the only the heavy elements remained. Okay, so that's cool. So in that sense, Mercury and the moon have a similar origin story, in that craters and impacts and things hitting it definitely developed it and helped it to shape it to what it is today. There's this here, Mercury's strange rotation. They thought maybe it was always pointed at the sun, for example, and this is just explaining how you can use the Doppler effect to determine the rotation of a planet. The faster it rotates, the more the velocity of it is smeared out, because you have, remember, the Doppler shift is a measurement of how fast something is moving towards you or away from you. So if you have a planet rotating, this part's coming towards you, so that's going to be slightly blue shifted. This part is not going to be moving at all towards or away from you, because the velocity will be perpendicular to you. And then this part is going to be moving away from you, so it's going to look like it's red shifted. So red shifted means it's going to look like it's moving away, blue shifted towards you, and then somewhere in between. So if it was just stationary, that's what you'd see. You'd see this nice spike, because it should have one velocity. If it has no rotation, it would look like that to begin with. Once it's rotating, the faster it rotates, some of it's going to be measured as going slower, some of it's going to be measured as going faster, some of it's going to be measured as right in between. So you end up building this kind of smeared out peak. So by looking at the shape of the rotation curve, then you can get the whether it's rotating. And so now we know that it's in this weird 2 to 3 stable orbit, where it rotates. Its day is about 60 days, and it's about 90 days to go around the sun. So it's like 2 to 3, a stable rotation thing like that with the gravity. So that's pretty cool. Yeah, Mercury shrank. That's pretty cool. And the origin comes from something hitting it. Okay, that's what I got. Let me know if you have any questions. See you guys later.